Okay, we're starting to look at differential equations, so a big part of calculus. You've already done some in Math 31, some of the basic ones. That's what we'll start with, and then we're looking at some other ones. So we've kind of grouped some examples here to see the different types. So first group, you can see dy dx, so the derivative is given with, and the derivative is with respect to the independent variable in each of these. So dx here, x, dt, t, dt, t. Okay, so those are some, and you've already done some similar ones, but these are a few more applications to practice. Then the next group that we'll learn how to solve, these dy dx, now this is your dependent variable. So R, R, H, H, V, V, capital T, capital T, capital Q, capital Q. Okay, and then the last group, both. You'll notice they're kind of in almost in ratio form, but both of these. Okay, so they're in terms of both of them. So examining those, how to describe them. The derivative is expressed in terms of, so the first group, the independent variable. Okay. The derivative is expressed in terms of the dependent variable. And the derivative is expressed in terms of both the dependent and independent variables. Okay. Oops. All right. So the solution to a differential equation is an algebraic equation that relates the two variables. The relation can then be used to answer specific questions concerning the variables. As you can probably see already, the solutions will involve antiderivatives, or integrals we'll use. The characteristics of the differential equation will indicate a method that can be used to find the solution. So we're going to start with those in group 1. So where the derivative is expressed in terms of the independent variable. So a very basic one. The slope of any tangent line to the graph of y equals f of x can be found by the slope equals 1 over x. So find the equation of f of x. Well, slope is dy dx, and we're told it's equal to 1 over x. So that means y will be equal to the integral of 1 over x dx. That's going to be ln of x plus c. Okay. Obviously, in this case, we know that x can't be 0, right, from that, because it wouldn't be defined. And so what does this mean here, right? So our original function f of x, this just means it's a vertical translation, right? So ln of x works, ln of x plus 1, ln of x plus 100, ln of x minus 300. All of those will have a slope of 1x because they're just vertical translations of y equals ln of x. Okay, pretty straightforward. Next one is a rodent, so like a mouse, has a mass of 30 grams at birth. It reaches maturity in 3 months. The rate of growth is modeled by the differential equation dm, where m is mass grams in, where m grams is the mass, so it's the mass in grams, would be a better way of saying it, and t months after birth. Find the mass of the rodent when the rodent is 2 months. So we are given some initial values here. So now, like in the last one, if we were given a point that it passed through, then we could find that c value. Here we are now given at times t equals 0, the mass is 30 grams. In any case, to get the mass, we're going to take the integral of 120 I'm a little crazy on my integrals. So, m equals integral 120 t minus 3 squared dt. So 120, that's going to be t minus 3 cubed over 3 plus c, all right, which is really 40 t minus 3 cubed plus c. And then we know, as I said, at t equals 0, the mass is 30. So now we can substitute 30 in, 0 in. Okay, and solve for c. So it's going to be 27 times 40, which is 1,080. It's going to be negative, because that was a negative 3, plus c. So c is 1,110. So therefore, your equation is m equals 40 t minus 3 cubed plus 1,110. And then remember, it asked to find the mass when the rodent is 2 months. Okay, and t is in months. So when t equals 2, m equals 40 times 2 minus 3 cubed plus, so that's going to be negative 40 plus, so 1,070 grams. Okay. So 1.07 kilograms. That's not a mouse. That's maybe a rat. Okay. Next one. A botanist makes a hypothesis that the rate of growth age of hothouse plants is proportional to the amount of daylight they receive. If t is the time in years after the shortest day of the year, the length of effective daylight per day is given by the formula. On the shortest day, the height of the plant is measured to be 123. 55 days later, value says what will its height be on the longest day of the year 6 months later. So this one's a little bit different in the fact that the word proportional is here. Okay, so we don't know, it's not exactly equal to that 12 minus 4 cos 2 pi t, it's proportional to that. So that means the rate of growth, dh dt, is equal to a factor of that function. Often we use k for a proportionality constant, so it's k times that. It's proportional to that. So we don't know what k is. It's a number, and we can figure it out as long as we have enough information given to us. So we need at least 2 pieces, whether it's the initial height and, well, usually it's initial and something else. It can be 2 different ones as well. Okay, so now h is if you want to put like brackets around that, you can, just to remind yourself. That's dt. Okay, so there's no variables here. So this is 12kt. T is the variable, right? Then minus 4k, because that k is distributed. And then integral of cos. So that's going to be sine of 2 pi t. Now really, you can substitute u in for 2 pi t, or you can do that in your head. This is going to be over 2 pi. Okay, and then plus c. Now, you can simplify that a little. The 2's divide out, but we know on the shortest day, okay, so t is the time in years after the shortest day. So shortest day is when t equals 0, and the height is 123. So we can put in 123, 12 k times 0 will be 0, minus, so that goes, divides out, so minus 2k sine of 2 pi times 0 over pi plus c. So that goes to 0. Sine of 0 is 0, so that goes to 0. So c is 123. Doesn't matter what k is. Write my equation, h equals 12 kt minus 2k sine 2 pi t all over pi plus 123. Now, we don't know what k is, but we are given another condition. So we're told 55 days later, the height is 128. So time is 55 days, but realize that time, t, is represented in years. So we actually have to show it as 55 over 365, and the height is 128. So now we'll substitute those in to get what our k value is, or proportionality constant. I'm going to just put the pi there, and then sine of 2 pi times 55 over 365 is 123. Okay, so you can use a calculator for this, so we'll bring the 123 over, that's 5. And then, I don't have a calculator on my screen, but use one. You can multiply this together. Simplify it, it ends up being 132 over 73. And then decimal form, okay, radian mode, sine of 2 pi times 55 over 365 days in a year is 0.8115, etc. And then you can use your calculator. So 5 equals, so 132 divided by 73, oops, 132 divided by 73 minus 2 times that answer for 0.8115, then don't forget to divide by pi. So you get 1.29157 k, all right, and then k will be 5 divided by that, so that's 3.8712. Show as many decimal places for right now. All right, and then says what will the height be on the longest day of the year, which is 6 months later. So what's the height when t equals 6 months out of 12? So that's 0.5. So your height is going to be 12 times that k value. And you can probably go to 4 decimal places is fine for right now. So sine of pi, remember, is 0. So this is going to go to 0. So really, if you have that previous answer that we got for our k value, multiply it by 12, divide by 2, or multiply by 0.5, and add 123. And then let's round to 1 decimal place. So that's going to be 146.2 centimeters. Okay, so 1.5 meters. So to summarize at the bottom, for the differential equations found in group 1, the rate of change in the dependent variable, so that's like y, with respect to the independent variable, is related to the independent. y dx is related to x. So now that you can do some of the practice questions in 23A. Okay. Now let's look at the next group.